Okay, so this presentation today is going to be an introductory presentation. So you can't cram 2 semesters worth of material in an hour. Very top level introductory. No equations will be shown. It's just going to be vague concepts backed up by a lot of hand waving. So that's the way I'm going. I am definitely not an expert, but I'm going to try to cover the basics in whatever time allows. I do have an ulterior motive here, and it's to familiarize you with as many of the common terms in the IC industry as possible. And with that thought in mind, I've included a glossary at the end of this presentation. You can go over yourself after this presentation's over. Okay, so the first thing I want to talk about is the term solid state and semiconductor. We've all heard these terms before, but where did they come from? I know we're familiar with them, but I wanted to give you some background on where they started. So way back in 1904, Doug probably remembers that, the first vacuum tube or thermonic valve was invented. And a few years later, the Audion, which is later called the triode, was invented, and that made modern radios possible. Over the next several decades, those breakthroughs led to many other vacuum tubes being developed for a whole variety of different purposes. However, all these vacuum tubes had a few things in common. They were large, they burned a lot of power, and they used electric fields to manipulate electron movement in a vacuum or near vacuum. So the concept of a field effect transistor was first patented by Austro-Hungarian-born physicist Julius Lilienfeld in 1925. I think that patent was actually in Canada. However, he was never able to build a working practical device based on that concept. However, in December of 1947, the first functional point contact transistor was built and tested at Bell Labs by John Bardeen, William Shockley, and Walter Pertan. And those three went on to win the Nobel Prize for Physics in 1956. In this picture I show on the right-hand side of the screen here, I'm not sure if it's the exact picture from 1947 or a replica, but that's what it looked like. It's a bunch of germanium crystals kind of pushed into each other with a bunch of wires hanging off of it. But that's the first transistor. That's how it all started. By the mid-1950s, transistors had been miniaturized and they were starting to replace vacuum tubes. And you can kind of look up in the upper right corner here, you can see what early transistors looked like. They were basically usually metal cans with 3 legs. Transistors made it possible to create new consumer products like the pocket radio by Texas Instruments, shown down in the lower right corner here. I think that was released for Christmas of 1954. I actually don't have one. So that radio had all of 4 transistors in it. You think about what a big step this is. This was the iPhone of the time. Prior to this, radios were big things that would sit on a table, and this was something that would fit in your pocket. It can only be done because the transistors, they burned less power, they were way more reliable, and transistors brought this product into fruition. Now, instead of manipulating the movement of electrons in a vacuum, transistors manipulate the movement of electrons in a solid. And that's why they're called solid-state devices, because it's manipulating in a solid, not a vacuum. That term solid state has gone on to describe, now we have solid-state hard drives. And solid-state hard drives store the bits on floating gate transistors as opposed to spinning magnetic disks. So that's why it's called a solid-state drive. Next, I'd like to talk about the term semiconductor, or just conductor in general. Well, we all know an electrical conductor is a substance or material that allows electricity to pass easily. In a conductor, electric charge, usually electrons, moves easily from one atom to another when a voltage is applied. And you probably recall from your high school chemistry class that the structure of an atom is a nucleus made up of protons and neutrons with a cloud of electrons swirling around it. In a neutral atom, the number of negatively charged electrons will equal the number of positively charged protons. And atomic theory and decades of experimentation have shown that electrons can only occupy certain energy levels or orbitals around the nucleus. And these are sometimes called orbital shells. And this causes the electrons to segregate into very specific energy bands. Here's an electron shell diagram for copper. Yeah, as we all know, copper is a great conductor. So copper is atomic element 29. So that means it has 29 protons and 29 electrons. And those 29 electrons get arranged in 4 shells or energy bands. And I'm showing a band diagram, or at least a shell diagram of what copper looks like here. Chemists have named for all these bands. However, they typically refer to the outermost band as the valence band. And you'll hear that term thrown around a lot, but it's the outermost band in the electron shell. So in a conductor like copper, the energy of an electron in the valence band is high enough such that the electron is also in what's known as the conduction band. And electrons in the conduction band have high enough energy to move freely throughout the material. So if we look at this energy band diagram again, you can kind of see, let me get my laser pointer up here. You can kind of see there's only one electron sitting up here in the valence band. Everybody else is down in these lower bands, but that one electron up in the valence band, it's free to move around. If there was another copper atom right next door, it could shuffle over to that copper atom, no problem, because it has enough energy that is considered up in the conduction band. Here's another way to draw these energy bands. And by the way, we've probably all heard this term band gap before. The band gap is the energy needed to kick an electron from the valence band up into the conduction band. In a conductor, there's no band gap in a conductor because the valence band and the conduction band, they overlap each other, just like this drawing down here. This allows electrons that are in the valence band to already move around easily from atom to atom, and because they're not bound tightly to any one atom. Insulators, on the other hand, are, as we all know, is a material that blocks or restricts the movement of electricity. If I drew the same diagram for an insulator, notice the band gap between the valence band and the conduction band is really big. This really prevents the valence band electrons from hopping up into the conduction band. This means the valence band electrons are bound very tightly to their parent atom, so they're really not free to roam at all. In a semiconductor, you have a relatively small band gap. This means it only takes a little bit of energy to kick an electron from the valence band up into the conduction band. And that unique property allows us to build electrical devices that can sometimes act as conductors, sometimes act as insulators. And that's really what you need if you want to build something like an on-off switch, which is what a transistor is. So why silicon? What's so special about silicon? There are lots of different semiconductors to pick from. I'm just showing some of the more common ones here. You can have elemental semiconductors. That means they're made from a single element, like silicon or germanium. You can also have compound semiconductors that are made from combining 2 elements or more, such as gallium arsenide, gallium nitride, silicon carbide. I hear there's even some work being done on organic semiconductors that are made mostly of polymer chains of carbon and hydrogen with some impurities added. I haven't heard a whole lot about those. Apparently they don't work all that great, but they're really inexpensive. So that might be something that's coming in the future. Of all these choices, why does silicon dominate the industry? I mean, all the other semiconductors are in use, but by far silicon has dominated this industry for, I don't know, 5 decades or so, maybe even longer. And the answer is similar to the fairy tale about the 3 bears. The band gap of silicon, which just happens to be about 1.1 electron volts, is just right. And what do I mean by that? Well, the valence electrons in the semiconductor only need a little bit of energy to pop up in the conduction band. And heat is a form of energy. If the temperature of a semiconductor gets too high, all those valence electrons get kicked up into the conduction band, and the material turns into a conductor. And that's not going to work for electronic devices. Can't shut anything off. Likewise, if the temperature gets too low, it may require too much energy to kick valence electrons up into the conduction band, and your material becomes an insulator, which also doesn't work for electronic devices. What we want is a semiconductor that will remain a semiconductor over a wide range of temperatures, and it turns out silicon is a great choice. It's not the only choice, but is a very good choice. The operating temperature range of silicon is roughly minus 60 C to 230 C, and that's minus 76 Fahrenheit to 446 Fahrenheit, a very wide range. By contrast, the operating temperature of germanium is roughly minus 65 C to plus 75 C. Now that's still a pretty big range, but you can kind of see at the top end of the range that plus 75 C somewhat limiting. So silicon also has a bunch of other advantages. First of all, it's a very common element. In fact, it's the second most common element in the Earth's crust after oxygen. So it's really not hard to find. Silicon also grows a native oxide, and that oxide is silicon dioxide, chemical formula SiO2, when it's exposed to oxygen. Now, in the early days, that native oxide made it more difficult to make good contact to silicon. However, that issue was eventually overcome, and now silicon dioxide in both its grown and its deposited form is commonly used as an insulator on modern ICs. And I just show a couple of instances here where it's used in its grown form. You typically grow an oxide for the gates of your MOS devices, which would be here, and you typically grow field oxide. It's also sometimes called LOCOS, which is local oxidation of silicon, or STI, which is shallow trench isolation. By contrast, gallium arsenide does not grow a native oxide easily. Therefore, any oxides needed to isolate areas in gallium arsenide, they need to be deposited, not grown. And that makes wafer processing somewhat more difficult, and it adds cost. Silicon also has the advantage that it's just a single element. You don't have to worry about getting the proportions just right like you do for a compound semiconductor like gallium arsenide. And this makes it a little less expensive to create the starting wafers. In addition, the electron and hole mobilities in silicon are both decent, and I'll talk more about mobilities in a minute here. This makes silicon an excellent choice for low-power CMOS circuits where you need both N devices and P devices. Gallium arsenide, on the other hand, has great electron mobility, but rather poor hole mobility, which means you really can't use gallium arsenide for CMOS circuits. So let's look at the atomic structure and the crystal structure of silicon. Silicon is atomic number 14. Again, that means it has 14 protons and 14 electrons. And it sits right here in column 14 of the periodic table. It used to be called column 4A in the old days. All the elements in that column have 4 valence electrons. You might notice carbon is right above silicon and germanium is right below silicon. So all the elements in that column there, they would like to form 4 bonds with neighboring atoms, just like carbon does in organic molecule chains. And if we look on this shell diagram off to the right here, you can see silicon has those 4 valence electrons right here. It would like to have 8 electrons in that outer shell. Typically, if you're trying to make a nice crystal out of silicon, this is the way it would be done. You'd have, let's say the blue atom in the middle here. You can see that if you arranged it nicely with other silicon atoms around it, you can actually share electrons with your neighbors. And these are called covalent bonds. Anytime you're sharing an electron to create a bond, that's called a covalent bond. So the blue silicon atom in the middle here is sharing 4 electrons with its next door neighbors. And this makes a nice, very structured crystal. So silicon's a great semiconductor. However, in its pure form, it really isn't all that useful. You really need to add some impurities to really make things happen. And these impurities are called dopant atoms. And there's 2 types, P for positive and N for negative. Let's look at the periodic table, columns 13 through 15, which is right in this area here. So silicon, we said, is in column 14. That's this column right in the middle here. And the elements used to dope silicon sit in either columns 13 or columns 15. The elements in column 13 have 3 valence electrons. That's 1 less than silicon. And we call those atoms acceptors or p-dopant. The elements in column 15 have 5 valence electrons. That's 1 more than silicon. We call those atoms n-dopant or donor atoms. Now, in practice, the most common dopants used today are boron for p-doping and phosphorus, arsenic, and antimony for n-doping. You kind of see I've highlighted those on the table here. The other elements in columns 13 and 15, well, they could potentially work. However, they have various disadvantages, such as undesirable activation energy, solid solubility, diffusion rates, a bunch of stuff I'm not even going to talk about today. But there's reasons that people don't use those other elements. I just really wanted to make you aware that the 4 most common ones by far are going to be phosphorus, boron, arsenic, and antimony. If you had phosphorus and you took a phosphorus atom and you inserted it into a silicon crystal lattice, what would it look like? Well, here's that phosphorus atom right in the middle. Now, phosphorus has 5 valence electrons. So 4 of them are going to share with the neighboring silicon atom. However, you've got this lone guy out here. He can't bond with anybody, so he's kind of a free electron. He's relatively free to move around, and he carries a negative charge. He's an electron. Similarly, if you put, say, a boron atom into a silicon lattice, it has 3 valence electrons. So those are going to bond with the adjacent silicon atoms, like we show here, but there's 1 bond that's left unfilled. And we call that unfilled bond a hole. And like I said, it's really not a hole, it's just the absence of an electron. Now, the hole has a positive charge, and it can move around in the crystal. The hole doesn't actually move, but it moves because an electron pops out of one location and jumps and fills that location, leaving a hole behind. So it looks like the hole moved. It was really the electron doing the moving, but the hole, it has to pop out of one spot and move to the other spot to make the hole actually appear to move. So by selectively adding dopant to a silicon crystal, we create either N regions or P regions. And the main carriers in the N regions are electrons. Electrons in the N region are called the majority carriers. I just want to get you guys used to this terminology. However, you could still have a small population of holes inside an N region, and those would be called the minority carriers. Minority carriers play an important role in some devices, like bipolar junction transistors. Unfortunately, I'm not going to get to talk about that today because of time limitations. Just be aware that sometimes minority carriers become important. Likewise, in a p-doped region, the majority charge carrier are holes. So you're going to have a lot of holes, and in a p-doped region, the minority carrier is electrons. So let's talk about doping concentration. In a pure crystal silicon lattice, there's about 1 × 10⁻22 atoms per cubic centimeter. If you add dopant to the crystal, you're going to be replacing some of those atoms. So the number of dopant atoms per cubic centimeter is called the doping concentration. Doping concentrations run from as low as maybe 1 × 10⁻13 atoms per cubic centimeter, maybe all the way up to 1 × 10⁻19. So the lightly doped regions are often referred to as P- or N-. You'll see this a lot, this terminology with the minus sign. Heavily doped regions are often referred to as P+ or N+, and they would be closer to the 1 × 10⁻18 or 19 atoms per cubic centimeter. So the term counterdoping or compensating refers to adding a higher concentration of one dopant into an area that's already been doped with a lower concentration of the opposite doping. And such is the drain and source of a MOS device. You can see here This material down below originally started out as low dope P. That's why it's got a P minus on it. But at some point in time, we diffused or implanted N plus in here to form the source and drain of this gate. And the N plus is much higher dope than the P minus. So it changed this region from a P region to an N region. That's called counterdoping or compensating. Resistivity. Resistivity is a measure of how resistant a material is to the flow of electrical current, and it's basically the inverse of conductivity. For example, copper has a very low resistivity since it easily allows electric current to flow. And insulators, on the other hand, have a very high resistivity since they block or resist the flow of electrical current. The resistivity of silicon varies with the doping concentration. Adding doping to a silicon lattice is basically adding electrical carriers. The more electrical carriers there are, the easier it is for electricity to flow and the lower the resistivity. This means higher doped regions, we're calling those P plus or N plus, they're going to have lower resistivity than lower doped regions, P minus or N minus. So electrons and holes both move through the silicon crystal, creating currents when an electric field is applied. However, they're going to move in opposite directions due to their opposite electrical charges. So given a positive electric field, the holes are going to move from the positive terminal toward the minus terminal, since opposites attract and like charges repel. Conversely, the electrons will move from the minus terminal to the plus terminal. Now, in both cases, electric current, which is defined as the direction of flow of positive charge, always flows plus to minus. But remember, the electrons flow one way, the holes flow the other way. Now we can talk about carrier mobility. The mobility of electrons or holes is basically a measure of how easily they move through the crystal lattice when an electric field is applied. And generally, electrons have higher mobility than holes. And in some ways, you kind of expect that. I mean, for a hole to move, it really needs an electron to pop out of one location, fill an existing hole, and then leave that new hole behind. Whereas an electron, if it's just a free electron, can kind of zip around, no problem. In silicon, the mobility of electrons are about 3 times greater than holes. This means the electrons will tend to move faster and easier than the holes do. And from an electronics point of view, this means devices that rely on the movement of electrons, like an NMOS device, will generally be more efficient and operate at higher speeds than devices that rely on the movement of holes, which would be a PMOS device. From a circuit design standpoint, this often shows up in the PMOS to NMOS W over L ratio. That's the width over length ratio of the transistor in an inverter. So if you have an inverter and you want the propagation delay through the inverter to be the same for the 0 to 1 transition as it is for the 1 to 0 transition, what you typically do is you typically make the PMOS device about 3 times the size of the NMOS device. And that's done to account for the mobility difference of holes in the PMOS device versus electrons in the NMOS device. We said in silicon that ratio of mobility for electrons to holes is about 3 to 1. If you look at gallium arsenide, it's 21 to 1. So there's no way you're going to use PMOS devices in gallium arsenide. They would just be way too big and way too slow. Let's talk about a PN junction. We discussed both P-doped regions and N-doped regions. However, what happens if you jam these two regions together? And that's called a PN junction. Both regions are electrically neutral. I mean, they start out electrically neutral. That means that the number of electrons and the number of protons in each region are about equal. Even though P region has some holes as electrical carriers, and the N region has some free electrons as electrical carriers, the regions themselves are electrically neutral. At least they start out that way. However, before I proceed with this, I wanted to take an aside and just talk briefly about diffusion. We'll come back to electrical devices in a minute. I'm sure you're probably all aware of this, but diffusion is a process that results from the random motion of molecules. And this is where matter moves from regions of higher concentration to regions of lower concentration until some equilibrium is achieved. An example of diffusion is easily seen if you place a drop of food coloring in a glass of water. Initially, the food coloring is going to be concentrated at the point of entry. However, if you don't shake it, you don't stir it, you don't do anything, just leave it sit there, and you wait long enough, the food coloring is going to equally disperse itself through the entire glass just due to the random motion of molecules. Holes and electrons want to do the same thing. They want to diffuse from regions of higher concentration to regions of lower concentration. So in a p-n junction, you have a high concentration of holes in the p material, and that wants to diffuse into the n region. And you have a high concentration of free electrons in the n region, and that wants to diffuse into the p region. And you can kind of see I've started showing that diffusion occurring here as they're moving across the junction, as the different carriers are moving across the junction here. As the holes and electrons diffuse, they carry charge with them. This causes the p region to become negatively charged because now we're moving a bunch of electrons in here, and it causes the n region to become positively charged because we're moving a bunch of holes into there. Remember, both these regions started out as electrically neutral. So this starts setting up an electric field, and the polarity of that electric field opposes the flow of the diffusion current, and we're going to get to that in just a second. When the holes from the p region diffuse into the n region, it's likely one of these free electrons in the n region is going to find the hole and is going to fill it. And likewise, when a free electron from the n region diffuses into the p region, it's likely to meet up with a hole and fill that hole. And you can kind of see I've circled electron hole pairs here that are going to join together, and the term for that is recombination. It's when a hole gets filled by an electron, and it eliminates both of the electrical carriers. However, any net charge is still left behind. The regions where all the electrical carriers have been recombined are referred to as depleted of carriers, and you've probably heard that term depletion region before, but all the carriers have been recombined. Holes have combined with electrons and gotten rid of the carriers, but charge is left behind. And that's called a depletion region. This electric field is going to continue to grow as you diffuse more and more holes one way and electrons the other way. However, eventually an equilibrium is reached when the diffusion current is exactly offset by an opposite current due to the electric field. And I think the term for that is drift current in the other direction. You can see what's happening here. The electrons want to diffuse right to left here, but they're repelled by the electric field, which wants them to go left to right. So eventually an equilibrium is reached at the p-n junction, and that happens when the electric field builds up to what's called the built-in potential. And it just so happens the built-in potential for a p-n junction in silicon is around 0.7 of a volt at room temperature. We're probably all familiar with that number. So what happens if you apply a voltage across the p-n junction? Well, it's going to depend on the polarity. We're all aware another name for a p-n junction is a diode. And the anode of the diode is the p region, and the cathode is the n region. So when the diode is forward biased, it acts to decrease the depletion region. And if you put enough forward bias on this diode, this depletion region collapses to almost nothing, and you start conducting right through the neutral regions here. You get a lot of current flow. If the diode is reverse biased, which is this diagram on the right, the width of the depletion region actually grows because of the voltage you're applying. That wide depletion region presents a very large potential barrier for any charge trying to flow across it. Therefore, the reverse current is very low. It's just a leakage current until breakdown voltage is reached. Breakdown voltage is going to depend on the width of this depletion region, and I'm going to talk more about that in just a minute. So doping concentration also affects the width of the depletion region. So in a higher doped region, you have more charge carriers per volume than a lower doped region. Therefore, the depletion region doesn't have to extend as deep into the high doped regions to produce that electric field, that 0.7 volt electric field. It only has to go a little bit into the high dope region. So let's look at, so in this drawing here, I show what a depletion region would look like if we put a high doped P plus region together with a low doped N minus region. So notice how the depletion region only moves a little bit into the P plus, but it goes pretty deep into the N minus region. The amount of charge on both sides here is equal. It's just you don't need to go as deep in the P plus because you have a lot more doping per volume in a high doped region. So the width of the depletion region also affects the reverse breakdown voltage of the junction. And the wider the total depletion region, the higher the reverse breakdown voltage. And so this slide kind of shows that. What you have here is, on the side, I've shown two very high doped regions pushed together here. So it's P plus to N plus. And you can see the depletion region is very small in this case. What you get is, from a VI characteristic, you get a very low breakdown voltage. This could be maybe somewhere in the range of 5 to 7 volts. It's very low. However, if you did a junction, say, from a P plus to an N minus region, now the depletion region extends pretty far into the N minus region. You got a lot of volume here, and the breakdown goes pretty far out. You can even go out further if you make them both fairly low doped. So if you wanted to have like a 200 volt device or a 400 volt device, any PN junction is going to have to be a very low dope junction. This is the Croft rule of thumb. The reverse breakdown voltage of a PN junction is going to be dominated by the lower doped of the two regions. Typically, you don't have two regions that have almost exactly the same dopant level touching each other. Usually they're at least an order of magnitude apart in doping concentration. So the width of the depletion region is almost always dominated by the lower doped of the two materials that you're putting together. And so is the breakdown voltage. Let's talk about junction capacitance. So the capacitance of a diode also depends on the width of the depletion region. And a very simple model for a junction capacitor is a parallel plate capacitor. And if you think of the P and N regions as being the plates of the capacitor, and the depletion region in the middle as being the dielectric, you can kind of see it really looks a lot like a parallel plate capacitor. Now the spacing between the plates is basically the width of the depletion region. And in a normal parallel plate capacitor, the further you move the plates apart, the lower the capacitance gets. For a very high dope junction, where the depletion region is very narrow, the capacitance per area is going to be pretty high. If you have a very low dope junction, where the depletion region is very wide, the capacitance per area of that junction is going to be pretty low. Next, I'd like to talk about resistors. And one of the more common devices used in an integrated circuit is a resistor. And there's a bunch of ways to make them. Many circuits use diffused or implanted resistors. This type of resistor is made by implanting or diffusing a region doped in either N or P material and then adding two contacts. So this drawing below here, this shows a P plus region that's been diffused into a wafer. We've added two contacts, terminal 1 and terminal 2, and there's a body contact here for the region, the N minus region below. How the resistor value changes with temperature is called the Tempco, temperature coefficient, or TC for short, of the resistor. And I'm just trying to get everyone up to speed on the terminology here. A positive TC means the resistor value increases as the temperature increases, and a negative TC is just the opposite. For many materials like metal, the resistance always increases with temperature because the increasing vibration, that means kinetic energy of the atoms at high temp, make it harder for electrons to move freely through the material without bumping into something. However, semiconductor materials can be different. The majority carriers in this P plus region that we made the resistor out of are holes. Now, as the temperature increases, the extra thermal energy, it can generate more carriers, and generating more electrical carriers are going to tend to lower the resistance of that region. However, just like in a metal, the higher temperature also increases the atomic vibration of the lattice, and that tends to make the resistance higher. So these two effects compete with each other. And depending on how the resistor is constructed, sometimes one wins, sometimes the other one wins. So this means you can have one type of resistor with a positive temperature coefficient, another type of resistor with a negative temperature coefficient, and maybe a third type with almost no temperature coefficient whatsoever. So by mixing and matching various resistor types, circuit designers can often generate whatever temperature coefficient they need for the circuit they want to build. You may have also noticed that there's a PN junction, a diode, in this resistor, and it's formed between the P plus region and the body of the underlying N minus material. So during normal operation, this diode is typically reverse biased to prevent current from flowing through it. However, that reverse bias junction creates a depletion region, and I'm showing what that depletion region would kind of look like over on the right-hand side here. So notice how the depletion region extends further into the N minus material, the lower material, than it does into the P plus material up on top. And that's because of the relative doping concentration, P plus to N minus. You don't extend as far into the high dope regions. So if you increase the reverse bias voltage on this junction, the depletion region expands both upward and downward. And as it expands upward, it eats into the P plus resistor a little bit. Because depletion regions don't have any carriers in them, that means you're reducing the channel width of this P plus resistor, so you end up increasing the value of the resistor. That's known as Voltco. So the voltage you apply to this resistor and the body contact can have an effect on the actual value of the resistor. And that's called voltage coefficient, or Voltco for short. Voltco of heavily doped resistors, P plus and N plus resistors, they're going to be small because the depletion regions can't extend very far into the high doped resistors. However, if you have a low doped resistor, you might see a greater Voltco because that depletion region can really extend deep into that resistor. Some resistors, such as polysilicon, I'm showing a polysilicon resistor shown below here, they don't have any junctions. They're just polysilicon surrounded by oxide. So there's no depletion region, and consequently, they don't have much of a Voltco at all. Maybe a little bit, but no junctions to deplete and cause the resistor cross-section to decrease. And FYI, I just drew this polysilicon resistor. I put some silicide under the metal contacts. Just for those of you that have never seen what silicide is before, it's a binary compound formed between silicon and metal, and it's usually left under the contacts to improve the contact resistance. So if you hear the term silicide, you know what it is now. It's a binary compound of silicon and metal. The next thing I want to talk about is ionization. Normal atom is electrically neutral. That means the number of protons and the number of electrons, they equal each other. An ion is created when the number of protons and electrons, they don't match. So an example of that is if you have a hydrogen with one proton and one electron, and you strip off the one electron, what you end up with is a positively charged hydrogen ion plus a free electron. So ions can be positively charged or they can be negatively charged. And they can be formed in many ways, such as during chemical reactions. However, in a silicon crystal, it's more common to generate ions through a process called impact ionization, where energetic charged particles create electron-hole pairs through collisions. And I know Corky and Nick have been talking about this a little bit from a space standpoint. And this just shows an energetic charged particle coming in here bumping into an electron, knocking it out, and leaving a hole behind. So the most common form of an impact ionization is caused by high energy electrons. And these electrons have been accelerated by high electric fields, and they're commonly known as hot electrons. You may have heard that term before. Hot electrons can be useful for lots of things, like programming the floating gates of EEPROMs inside your phone or your flash drive. That's how you store all those pictures on your phone in something that looks like an EEPROM. And they get there through hot electrons. However, hot electrons can also cause reliability concerns by causing unwanted threshold shifts in MOS devices due to charge accumulating in the gate oxide. And this is a topic for another talk, but all these free electrons that are bumped around, if they get bumped up and they stop in the gate oxide and they deposit a charge there, you can slowly shift the threshold voltage of your MOS device as you accumulate more charge in that gate oxide. In space, impact ionization can also occur from energetic particles. We're calling those cosmic rays. I know that's not the greatest term, but I think that's the term everybody uses for energetic charged particles in space. Those particles can come in and they can cause ionization events very similar to the hot electrons. If they come in and they create electron hole pairs in a gate oxide of a MOS device, the electrons tend to go away, but the holes tend to stick around, and you get the oxide slowly over time accumulating positive charge. The MOS thresholds will change over time. Now, if those collisions occur in a silicon crystal, a different effect is observed. If an energetic particle passes through a silicon crystal, it creates a somewhat linear trail of electron hole pairs as it loses energy here. And you can see it's creating electron hole pairs all the way through here. And this is known as LET, or linear energy transfer. I know Corky and Nick have talked about this, again, at great length, probably in much more detail than I can provide here. Higher energy particles are going to have higher LET numbers. Now, if that trail just happens to pass through a PN junction, the built-in potential of that junction and any other external voltages applied to that junction, well, they're going to tend to sweep the electrons in one direction and the holes in another direction. And that creates a very short transient pulse of electrical current. And that's known as an SET, or single event transient. Now, SETs are only going to occur at PN junctions. However, the odds of a double event, that means two unrelated PN junctions getting hit by energetic charged particles at the same time, that's very, very low. Therefore, circuit designers typically only concentrate on protecting integrated circuits against single events, not double events or triple events. So an SET event is simulated either as a short burst of current or maybe as a resistor that shorts out the junction for a brief period of time. You can see a representation over here. Let's say we have this PN diode here, and we want to simulate what happens if it gets struck by an energetic charged particle. Well, we model that as a little short burst of current here that is basically across this reverse bias junction. So designers, they can look at every PN junction on the chip, and they can simulate the results from these SETs, one junction at a time. That can get really tedious. Fortunately, we're developing better tools all the time that allow us to make this chore a little bit easier to do. But it's still something that takes up a lot of time, and there can be hundreds of thousands of junctions that you got to look at. So you're not going to do it manually. Some passive devices like polyresistors or MIM capacitors, MIM means metal insulating metal, they don't have any PN junctions in them. And that makes them relatively immune to SET effects. And designers will try to take advantage of that. If you can use one of these devices instead of a device that has a junction, you're going to try to use one of these devices if you can. Now, for active devices like transistors with lots of junctions, several methods are employed to mitigate the effects of SET events. And I just showed two of the more common effects or ways to do it here. One way is we use RC filtering to kind of smooth out that current pulse that we get when a charged particle passes through a junction. Another way is we use redundant logic. And if you have three identical sets of logic here, and they all go into a voter, and if one of these get hit and produce the wrong 1 or 0, well, as long as these other two are okay, the voter still produces the correct value. These two methods are very commonly used as ways of mitigating the effects of SETs on a circuit. Simulations are never perfect, and sometimes our predictions are off. So we really have to verify SET simulations by doing actual testing on units under a real particle beam. And we use Texas A&M cyclotron facility for this. And yeah, thank you, Eric, for all the work you do at that facility. I appreciate it. Last topic I'm going to have time for today is, and I wish I could have time to talk about transistors, but not today, sorry. Single crystal versus polysilicon. So a crystal is defined as a solid with an orderly arrangement of atoms. And in an earlier slide, I presented an arrangement of crystalline silicon where each silicon atom bonded with 4 of its neighbors. However, silicon can also exist in what's called a polycrystalline form. They're both silicon, and the only difference is the arrangement of atoms. And this other form is called polysilicon, or just poly for short. Once again, poly is a type of silicon, single crystal is a type of silicon. The only difference is how the atoms get arranged. In single crystal silicon, the atoms are very orderly, like soldiers marching in a parade. In polycrystalline silicon, the atoms are arranged more like a pile of building blocks. So inside each building block, it could be fairly orderly, but from block to block to block, it kind of gets jumbled. Poly in Latin means many. Therefore, polycrystalline silicon means silicon with many crystals. Now, both types of silicon are used extensively in integrated circuits. Silicon crystals typically used for the actual building of the electronic devices because you get the best and most consistent device performance using regular crystal. The devices match better, the leakage currents are lower. Generally, everything performs way better with single crystal silicon. However, polysilicon is generally used for other things like the self-aligned gates of MOSFETs as an interconnect, or maybe as a material for filling trenches on the wafer. Polysilicon is much easier to create because you don't have to worry about lining up all those atoms. You just let the atoms fall where they want to. Single crystal silicon, on the other hand, requires a special process to generate it in bulk. And there are 2 different processes used for generating single crystal silicon. The ingots that are grown are also called boules, and I believe the term boule in French means a round loaf of bread. So the first of these techniques is called the, and I'm gonna mess this name up, Trochowski process. My Polish is really bad, so I'm just going to call it the CZ process for short. So it's named after this Polish scientist who developed it in 1916. And the second process is the float zone method. So in the CZ process, you start by inserting a seed crystal into a melt of silicon that's in a crucible. And you're rotating this and very slowly pull the seed crystal out. And what happens is the atoms from the melt cling to the seed and they arrange themselves to match the crystal structure of the seed, growing more crystal as the seed is pulled out. And you can see what you get down here is a silicon boule or wafer. And just so happens to have the top of one of these silicon boules here. You're welcome to come up and see this afterwards. This is all single crystal silicon right here. Here's another piece of one that's been chopped off. So in the float zone technique, you start with a rod of polysilicon, but you still have a seed crystal down at the bottom here. And now you have some RF heaters that start at the lower end of this rod, and they work their way up melting a zone or molten portion of the rod and refreezing it all as it goes up. As this molten portion of the rod refreezes, the polysilicon, the atoms from that polysilicon realign themselves to match the crystal, and you end up with single crystal silicon down below. So again, these RF heaters will move from the low end of the rod to the high end of the rod. When you're all done, you end up with a rod of single crystal silicon. Now, each of these methods has its own set of advantages and disadvantages, which I'm really not going to get into today. And they're both still in use right today. So these are both kind of common. I wanted to show a slide to show what the silicon wafer size progression has looked like over the years. And this starts way back in the 60s, somewhere in the 1 inch to 1 1/4 inch wafers. That's a 30 millimeter wafer. And in the early 2000s, they started making 12-inch wafers. And I think there are some facilities now that are actually using 18-inch wafers. I mean, we're talking something about that size. I show a large silicon bowl off to the side here that I managed to get a picture of. I do have a 12-inch wafer with me here, if I can get it. That's what a 12-inch wafer looks like if you've never seen one. I don't have an 18-inch, sorry. I also have a 1 1/4 inch wafer if you'd like to see a 1 1/4 inch wafer. Not too many of these left. Okay, so summarize the talk. Modern semiconductor devices, they control the flow of electrons in solids. And it's been close to 75 years since the first functional transistor was demonstrated. Since then, a lot of breakthroughs in physics, manufacturing, and just the industry in general have occurred to advance this industry. However, we owe a lot of gratitude to those early pioneers without whom the modern world, cell phones, microprocessors, satellites, and most importantly, my job wouldn't exist. Thank you for your attention. I'll take some questions, and you can look through this glossary of terms at the end here if you want.